We can also do problems where we're doing both the derivative and the integral. So let's say that capital F of x equals the integral from 3 to x of 4 t cubed dt. What we're going to do is we're going to find the derivative with respect to x of this capital F of x. So the first thing we can do is just our normal f of x. The antiderivative of 4t cubed is 4t to the 4th divided by 4. And our bounds are x to 3. So we've got x to the 4th minus 3 to the 4th, where f of x equals x to the 4th minus 3 times 3 is 9, 9 times 9 is 81. Now, when we go and take the derivative again, when we take the derivative here, we're going to bring down that 4, subtract 1 from the exponent, and then the derivative of a number is just 0. So we just end up right there. Notice something really interesting. This right here is the same thing that we started out with, except that this t has been replaced by an x. And that makes a lot of sense because when we put in this number for the bound, we're going to get out just a plain old number. And when we take the derivative, that part goes away again because the derivative of any number, regardless of what it is going to be 0. And here, when we're doing the integral, the first thing we do is take the antiderivative. And when we take the derivative of that, we end up back where we started, right here. So this is actually something that can be generalized to create what's called the second fundamental theorem of calculus. The derivative of the integral from a to x, where a is any constant number, f of t dt equals f of x. So this just says when we take the integral with variable bounds, should say a variable for a bound, and then take the derivative, the result is the original function with the variable replaced. Notice this is only true if this is a variable. If these are both numbers, then we've seen before what we come up with at the end when we take the integral, so we come up with a number. When we take the derivative of any number, it's 0. So if we have the derivative of integral where these are not variables, the derivative is always going to be 0. This only is true when we have a variable for one of our bounds. So this makes for a very, very nice shortcut for problems like this. Find the derivative of g of x if g of x equals the integral from negative 100 to x of the following: root 3t minus 7 over the cosecant of t minus 1 with respect to t. Now one thing we could do is we could do our usual how to take the integral and try to figure out the antiderivative of this and plug in x and plug in negative 100 and subtract them and all that kind of thing. The problem is this is going to be a huge pain in the neck because we actually don't have a formula for the antiderivative of the cosecant of t, and this is just a huge monster. But what we can use is we can see that we're going to take the integral and then we're going to take the derivative again to get g prime. So when we do that, when we take the integral and then take the derivative again, we just end up with the original function, but this variable has been replaced by this variable. So we can just look here and say g of x is going to be this original thing, but we replace the t with an x. Done. Way faster than anything else we could do. We can also use that property if we are finding the derivative at a particular value of x. This is our final problem. Find f of 1, actually f prime of 1, if f of x equals the integral from 7 to x of 3t squared over 7t minus 8. Looks like it might be doable to find the antiderivative of that, but we don't have to because we're taking the integral and then we're taking the derivative again. So we can just say that f of x equals 3x squared over 7x minus 8, or I should say that's f prime. So f prime of 1 just means we put 1 in for the x,